put your maths teacher hat on for a second, okay? Maybe you're like, I don't have a maths teacher hat. Well, get one and then put it on. Now, if I gave you this function and I drew this graph, what kind of volume could we make with it? You can make a couple of different kinds, couldn't you? Probably 2, 3, you would say, well, you can either choose this axis to rotate around, and that would give you sort of a nice, well, it's something like a ball, but it's got sharp points at the ends. I suppose you could do it the other way, right? And it would look like one of those upside down chiffon cake type things, okay? And you'd get these annular type discs, right? But that's all very pedestrian for me. I want us to move a little further, right? Rotating just around the axes, that's so 2013, okay? We can move past that. Let's rotate around something else. Tell me, what's that point there? What's that value? Have a look at it. Come on, you know. Stationary point at x equals 2. When I put x equals 2 into there, it looks like I get 4, right? Okay, well if that's 4, let's pick a point, or rather let's pick a line, like y equals 6. There's a line, it's straight, relax, it's not that hard. What if we rotate it around this? Okay. Now what shape would you get? Well, don't forget, right, this is the area under the curve, right? This area under here. Okay, so that's what's going to rotate around. It's going to go all the way up to the top, right? If that's 6, you're going to get 8, 10, 12. So you'll have something like this. Up the top, right? I'm looking at it straight on. Okay. Now, because I'm rotating this area down here, right? What's going to be in the middle? Space, right? There'll be nothing there. It'll be hollow, okay? But these two parts are going to connect, aren't they? Can you see it? It looks like a yo-yo to me. Well, you're thinking of the inside, which is actually hollow, right? So I actually want the outside of the yo-yo. Is that okay? A weird kind of shape, but that's what happens when you rotate around somewhere awkward. Okay? Now, just pause for a minute and think about how you would approach this with this technique. What would you do? I'm guessing you would want to think about the whole cylinder, right? The whole cylinder. And then you would subtract the middle part, because we just said that was hollow, didn't we, right? And so you would have to fashion some way to work out what that middle part is, right? That's tricky. That's quite difficult to approach it that way. But we have a new tool in our tool belt now, right? Think about this. What would you get if this was your shape? Let's draw it. Let's pick a point. Pick one up in the middle, because that'll give us something nice and easy to visualize, okay? So if I sliced it perpendicular to the axis of rotation, right? It's no big deal that the axis has been moved off the x-axis, right? I can still go perpendicular. I'll get a shape like this, for instance. Yeah, that's hard. It's all clouded in the middle there. I'm going to draw it off on the side just so I can really see what's going on. Okay, so move this guy over for a second. Okay, I want to know what this annular disc looks like, this annular slice. Like this. Okay, there you go. Now I can see it a little bit clearer. Now what I did before, all I needed to know was an inner radius and an outer radius. And then you can work out the volume, no problem, okay? So what are the inner and outer radii here? You know, here's my, might be easier if I go down actually. Here is my little r, right? And here is my big R. Okay. Which is easiest to work out?
Little r.
Little r? What's little r? Now, I think little r kind of depends on big R. Here's what I mean. Think about different kinds of slices we could take and the different values that big R will take. Okay, think about it. Right, this is our whole shape. If I move this slice over to the edge, for instance, what would big R be? It'd be Well, it'd be 6, wouldn't it? Now if I come somewhere into the middle, like where I've drawn, what's big R? It's still 6. That's interesting. So your outer radius is constant. That's nice. Okay. Now to work out what little r is, see that thing's changing, isn't it? But we don't have little r as a function. Look, it's up off the axis, right? But what I do have a function for is this guy. I know what that is, right? Because that's been defined as 4x minus x squared, right? Just for now, I'm just going to call it y rather than write that because that's a bit awkward. Okay. Now, if this here, which is not the inner radius, right? If that's y, then what should this be? It'll be the difference, 6 minus y, right? I might leave that little r there actually. 6 minus y. Okay, there you go. I can deal with this. I can deal with this, right? The volume I'm going to get from here, right? The volume is the integral from, now how far am I going? From 0 to 4. 0 to 4. Of, now, what is the volume of the annulus, right? Pi big 1 minus little 1 with respect to x. Okay? Now, what am I going to get here? Let's see. We already established that the big R is just 6, so that's 36. Okay? What's little r? It's 6 minus y. 6 minus y all squared. 6 minus y all squared. That sounds like 36 minus 12y plus y squared. Is that okay? That's my little r squared with respect to x. Can you see now why I'm still keeping it in terms of y's? I could put it in terms of x's, but when I do this, it's just going to sort of explode. I want to do as much simplifying as I can before I stick x in. 36's cancel, don't they? And I might as well stick the pi out the front while I'm at it. Those go, bang, bang. Double negative, negative positive. Now, keeping in mind that we know exactly what y is, it is well defined, right? And it's not something gross. I can put that in, it'll expand out, and then it's just a polynomial. I can integrate that, right? Think about this. Remember how 5 minutes ago we said, how would we approach this volume using this? And it's weird and it's awkward, and you have to come up with tricks in order to work out what this volume is in the middle, right? But if you consider it just by slices, what do the slices look like? I don't care where the slices are, I know exactly what its volume will be, right? And so that's why it gets to this step, and you're like, this is just integration like it was before. Okay? So let's just finish it off, shall we? What am I going to get? Pi, 0 to 4. Okay, that's 4x minus x squared. That's 4x minus x squared. With respect to x, it's all in x's now. You can crunch the numbers, can't you? That's all that's left, number crunching. Right? So I think when you simplify out, you expand here and collect like terms, you'll end up with that. And this is a trivial problem for us, right? You can just integrate that, evaluate. You know, it's even nice and neat because all of these have x terms in them. So when you evaluate at 0, that just disappears. So all you're interested in really is the upper bound. Very simple problem, okay? So this idea, which looked very unimpressive before, right? Just a subtle shift, thinking about rather than 2 big volumes and you subtract one from the other, versus thinking about the slices individually and then adding up a whole bunch of them. Sometimes, no difference. Why bother? Other times, incredibly powerful and time-saving.